The Casio ClassWiz calculator lets you do lots and lots of things with statistical distributions. So we're going to look at a few of those things now and hopefully talk through how they work, because it's not immediately obvious from the calculator screen exactly what's being calculated and how you might use it. So let's start by going to the menu setup button, and then we can choose between these different modes. Number 7 is the one for statistical distributions. You'll recognize it because it's got a picture that looks a lot like the normal distribution curve on it. So you can either navigate with the arrows, or you can just press the number 7 and you'll jump straight to it. Now what you'll notice here, you've got a few things in the menu. You can scroll up and down and see them all. On the first page is normal PD, normal CD, inverse normal, and then binomial PD, following on to binomial CD on the next page, Poisson PD and Poisson CD. Now, to save you some time, there are a few of these that you will never need at A-level maths. So the very first one, normal PD, we never use. That's the probability density function for the normal distribution. So down here, you can see the normal PD. It's something to do with the height of the normal distribution curve. You can think of it as how tightly packed the area is within the range and of that particular number. We don't use it because whenever we want to do things with a normal distribution, we either want to find the area or we want to work backwards from the known probability, the known area, to a particular value, an upper bound. Normal CD we'll use every time we want to find a probability from a normal distribution curve. Inverse normal when we're trying to work backwards from a probability. Binomial PD is for solving equals problems with a binomial distribution. And when we scroll down, binomial CD is for solving less than or equal to problems with a binomial distribution. Poisson is a different discrete probability distribution. So in some ways it's more similar to binomial than it is to normal, but it's not something you need to worry about for A-level maths. So I'm not going to talk about those. You shouldn't be needing those two modes for A-level maths. So let's start with normal CD. We would choose option 2. And we've got 4 things that we need to fill in: lower, upper, sigma, and then if you go down, you'll get mu at the bottom. So those 4 things we've also got over here, so you can see them all in one place: lower, upper, sigma, and mu. These are the values that correspond to a probability question. Here's an example down here. So if x is normally distributed with a mean of 0 and a standard deviation of 1, then I'm asking the question, what's the probability that x is between -2 and 2? So we can change our bounds, and we can also change the standard deviation and the mean. Be careful here, because although often we refer to a normal distribution with the mean and then the standard deviation, on the calculator it's the other way around. It's very easy to get them mixed up. So you just type in your numbers. If we have a lower bound of 5, type in 5, press equals. An upper bound of 6, type in 6, press equals. Maybe we've got a standard deviation of 3 and we've got a mean of 4. And then when you press equals for the last time, it should give you a probability. P equals 0.116948819. So we've got roughly an 11.7% chance. Now, if you press equals again, it'll take you right back to the screen you were on, so you can check that you've put the right things in. Common mistake I make is getting mu and sigma the wrong way around. You can also check if you're using a situation where the lower bound doesn't exist. Perhaps you're saying, what's the probability that x is below 5? Well, you can mess with the size of the lower bound to make sure it's low enough that it encompasses everything below 5 without any lower limit at all. So let's say, for instance, we're thinking about this scenario where we're looking at SAT scores in America, where the average is 400 and the standard deviation is 100, and we want to know the probability that someone has a score that is no greater than 350. We put that in as the upper bound, but for the lower bound we might use a number like 0. So on the calculator you put 0 for the lower bound, press equals, put 350 for your upper bound, press equals, and then we'll need 100 for the standard deviation, 400 for the mean. And if you make a mistake, you can always go back. So if the number doesn't look sensible, you can go back and double check that what you've put in makes sense. and we get a probability of 0.308 something. Now that was with a value of 0 for our lower bound. That's not technically the same as saying the probability being less than 350. It's actually more like this, the probability of being between 0 and 350. But in reality, if we had a much lower number, like minus 1,000, it doesn't change the number that much. So if you look at what the calculator is giving for 0, minus 308505 something, minus 308537 something. Slightly bigger, but the only change is within the 5th decimal place here. So given that you're likely to give your answers correct to 3 significant figures, it's not going to make much difference. A good rule of thumb is to be more than 4 or 5 standard deviations from the mean. So going down to 0 from 350 wasn't quite far enough to have no effect on this number, but it was far enough that it had a very small effect. If in doubt, you go back and you change your lower bound to something much lower, like negative 1,000. It's not possible to get a value as low as negative 1,000, so it's definitely low enough, and it'll be equivalent to a much lower number. You could put in a number as low as you like, and there's going to be no change to 8 or 9 decimal places on here. So that's normal CD mode. The next mode we can look at, if we go back to menu and we choose option 7, is inverse normal. We would use this anytime we're trying to go backwards from a known probability to an unknown upper bound. So you'll notice straight away we've got sigma and mu carried over from the time that we were working on normal CD. This is quite helpful if you're ever going back and forth with problems going forwards and backwards. Sometimes you're working out a probability, sometimes you already know a probability. We can put a number in here like 0.9 for the area. And the area, remember, corresponds to the probability. So if we look here where we've got inverse normal in the spreadsheet version, it tells us that the probability that x is less than 1.28 is equal to 90%. What that's saying is, here's the 1.28 that you would need for your upper bound in order to have an area below that point of 0.9. Now, if we make our standard deviation and mean the same as the one we've got on the calculator, we'll see what it's giving us here, 528. That's basically saying if you get a score of 528 on your SAT, then you are in the top 10% effectively. The probability of someone getting a score lower than that is 90%, which is equivalent to saying the probability of someone getting a score higher is 10%. We can also use inverse normal if we're dealing with questions where we don't know the mean or the standard deviation, or perhaps we know one but not the other. Classic way to do that is to change the standard deviation here to 1 and change the mean to 0. The nice thing about this is that now, if you've got a number that is 3 standard deviations above the mean, well, if the mean is 0 and the standard deviation is 1, 3 standard deviations above the mean is just 3. And if you're 1.5 standard deviations below the mean, it'll just be minus 1.5. So when we use this, that 1.28 tells us that for any normal distribution, you need to be 1.28 standard deviations above the mean in order to have 90% of the values below that number. So 90% of people will be no taller than 1.28 standard deviations above the mean height. 90% of SAT scores will be no greater than 1.28 standard deviations above the mean SAT score. It's one of the fundamental properties of the normal distribution curves, and we can apply that to lots of different situations. So if you had 2 pieces of information, you could use those 2 to construct simultaneous equations. Let's say, for instance, that you knew that there was a 20% chance of a sunflower growing to a height of more than 2 meters. Well, that means there's an 80% chance that your sunflower would grow to a height of 2 meters or less. So you could use a 1 and a 0 in your inverse normal and calculate the probability, calculate the value, the upper bound that belongs with the probability of 80%. And it comes out as 0.841. In other words, 0.841 standard deviations above the mean. Now, that gives you one clue, but it doesn't give you the complete description of what's going on. In order to do that, you'd need a second piece of information. Maybe we know that 5% of sunflowers are shorter than 0.5 meters. So we'd say 5% of sunflowers, that's 0.05, and they are shorter than 0.5 meters, means that this number corresponds to 0.5 meters. But this means 1.64 standard deviations below the mean. And at this point, you could then go back to the menu setup. You could choose option A, which is this button here, and then solve your simultaneous equations in here. Two unknowns. You've got to be careful to recognize that x and y are in reality mu and sigma. But if you've got the mean, then we press equals, and we have 0.841 standard deviations above the mean. If we're told that that's equal to 2 meters, we can put a 2 in there. And then for the other one we had, I think we said that 5% of sunflowers are below a certain height. That corresponds to minus 1.64. So 1.64 standard deviations below the mean. We have 1 times the mean minus 1.64 times the standard deviation. And that would equal, well, we said half a meter, so we could put in 0.5. Then the solutions we get correspond to the values of mu and sigma. The first one, x, we can press SD and get that as a more sensible value. That must be the mean. So the mean height of a sunflower, according to those two stats that we came up with, is 1.49 meters. Press equals, we get this standard deviation of sunflower heights, which is 0.6 meters. And then you can check by drawing yourself a quick sketch to see if those numbers seem to make sense. Now, back to the statistical distributions. Binomial PD is the next one on our list. If we choose option 4, straight away we've got two choices, list or variable. Now, variable is the simpler one to look at, so we'll start with that. That's number 2. And we have just 3 numbers to fill in. And this is the same as what we're looking at here. So if you decided that you were going to toss a coin 12 times and you thought it was a fair coin, so we'll keep it as 0.5 for the probability, you're asking the question, how likely is it that we get exactly 6 tails? Seems the most likely result, so that should be the highest number. Then you could just put in 6 for x, you put in 12 for the total number of trials, you put in 0.5 for the probability, press equals, and there's the probability. Now, as you can see from over here in purple, what we're calculating is the probability that your discrete random variable is equal to 6. It's the chance of getting exactly 6 tails when you toss a coin 12 times. And this is the one that you could calculate yourself directly using the binomial formula. In fact, the NCR button is down here on the calculator. So if you wanted to do this directly for yourself for some reason, or if perhaps you are working on a problem that required something more than just directly calculating with the shortcut functions that the calculator gives, then the process will be something like, we need to know the total number of ways to choose 6 items from 12. 12 choose 6, that's the binomial coefficient. That's the number of different ways that you could get 6 tails out of 12 coin tosses. They don't all have to come at once. You could have head, tail, tail, head, tail, tail, head, and so on. There's lots of different ways that can happen, 924 to be precise. You'd multiply that number by the probability of success to the power of the number of successes, and then you'd multiply by the probability of failure to the power of the number of failures. In this case, those both happen to be the same, and out comes the number 0.22558. It's exactly the same. That's all that's going on behind the scenes with binomial PD. So it's handy to have. It saves us having to write in those numbers, but it's not essential. Another quick example, if we had a 4-sided dice, a tetrahedral dice, then there's a 0.25 probability of it landing on a 4, let's say. If we do it 20 times, how likely is it that we get 3 4s? And the equivalent, if we were doing this longhand, would be to say 20 choose 3. That's the total number of ways to choose which of the 20 rolls happen to be 4s, multiplied by the probability of getting a 4, 0.25, to the power of the number of 4s we got, which is 3, multiplied by the probability of not getting a 4, 0.75, to the power of the number of times we didn't get a 4, 17. 0.1338. And as you can see over here, that's exactly the same result we get from Binomial PD. So it's handy because it will give us the result more quickly. We don't have to memorize this formula. We can just make use of the calculator function. The one that's essential is Binomial CD, because when we use Binomial CD, we are taking advantage of the fact that the calculator can do lots and lots of that type of calculation we've just done over and over again and add them all together for us. So again, we'll go with the variable mode here, and it looks very similar. So the thing to be careful of here is that CD is the only clue on the screen that we're doing something different to Binomial PD. If we entered the same numbers, 3, 20, and 0.25, we get a different answer. Now in this case, the answer is not wildly different, but it is a little bit different, and it's because the calculation that's being done is a cumulative distribution. So we're looking at the cumulative probabilities. That 0.225 tells you the probability of getting either 3 4s or 2 4s or 1 4 or 0 4s. So it's giving you the probability, as it says down here in purple, of x being less than or equal to 3. Binomial PD answers the question, how likely is it that x is equal to a particular value? Binomial CD answers the question, how likely is it that x is no greater than a certain value? So a little bit like with inverse normal, where the number it gives you is the upper bound, with Binomial CD, the default is that the number we put in is an upper bound, an inclusive upper bound, so it's less than or equal to this number, and then the probability that comes out is going to be the combined effect of the probability of getting 0, 1, 2, or 3 successes in this case. That can be really helpful if we want to know how likely it is that we get at least 6 tails when we toss a coin 10 times. Well, at least 6 is the opposite of 5 or less. So we would say the probability of getting 5 or fewer, and then we toss a coin 10 times. This is a fair coin, so we'll change the probability to 0.5. The answer here is telling us how likely it is that we get 5 or fewer tails, which means the probability of getting 6 or more must be 1 minus this number. Now, one slightly awkward thing about the calculator here, we're in stats mode as opposed to basic calculation mode, which means we can't directly do calculations with this number. But the calculator will still remember whatever the most recent value was. So if we click menu setup and go to option number 1, the one with the plus, minus, divide, times, we choose option 1, we're back in calculator mode. And now if you press the answer button at the bottom and press equals, the number you had before from stats mode is still saved on there, which means you can do 1 minus your answer and out pops the number you're interested in. So if you were only able to calculate the probability of something not happening, you can do 1 minus that number and you've got the probability of that something happening. Now the last thing I briefly want to look at is the list option for Binomial PD and Binomial CD. It's particularly nice if you're trying to get a feel for a distribution. Let's say we're going to toss a coin 5 times. Then I might be interested in the chance of getting no tails, maybe 1 tail, 2 tails, 3 tails, 4 tails, or 5 tails. After I enter each number and press equals, at the end I press equals one more time, and it gives me the option to set the value of n and the value of p. So if I'm thinking of a coin toss that happens 5 times, I'll put n equal to 5, the number of trials. If it's a fair coin toss, I'll set p equal to 0.5, and I'll press equals one more time. And now what you're looking at is basically what Binomial PD does, but as many times as you like. You can scroll up and down this list and investigate how the probability changes. So you can see that the probability of getting no tails is only about 3%. The probability of getting 1 tail is more like 16%. Goes up to about 30-something% for 2 tails or 3 tails. They're both the same. In fact, if you scroll to the right, if you move to the right with your arrow keys, you can see they're exactly 0.3125. This one's 0.15625, so it's truncated that number. It's not rounded, but it is truncated to 4 decimal places, so that you can see the exact value if you hover over it, you put your cursor exactly over that number. Similarly with the last number there, which is 0.03125. So you can get those precise numbers on the screen if you need to by scrolling up and down there. If you find you want to investigate other values, you can type these in even after you've filled some in. So I could try 6. It's not going to give me anything sensible here, but you'll notice I have to press equals a couple more times to get the results refreshed. 6 is giving a 0 because it's impossible to get 6 tails when you toss a coin 5 times. But if we change this to maybe 7 coin tosses, and perhaps we've got a biased coin, so it's actually got a 60% chance, we can then go back and we've got the whole thing refreshed and we can look at the result now. Very low probability of getting no tails because it's a biased coin and we've tossed it quite a few times. And then the probabilities increase as we go along. We can see the modal value is actually 4. That comes out as about 29%, whereas the next most likely is 5, which is 26%. And you can see each of these as you go along. We could include 7 if we wanted to. Press equals a couple more times, and it gets refreshed. You can move straight to the bottom of your list by pressing the up arrow when you're at the top, so that's helpful as well, especially if you've got a long list. Exactly the same thing happens in Binomial CD mode, so you'd have to scroll down and then choose option 1. And then if you go for list, what we're going to see now is a cumulative distribution. So if I use exactly the same one I had before, you'll find the numbers are different. They are always increasing. And that's because when we get to, for instance, 5, that 0.84 something, that's the probability of 5 or fewer successes. So of course, each new number is going to be bigger. It's a cumulative value. By the time we get to 7, the question is, how likely is it that we get 7 or fewer tails when we toss a coin 7 times? And of course, the answer is 100%. Something is going to have to happen between 0 and 7 tails, so it makes sense that that's going to be 100%. Hopefully, that's been beneficial. It can be hard to make sense of exactly what the calculator mode is useful for, so this little screen here with the extra detail might give you some useful clues. Remember, we don't need to make use of normal PD mode, and we don't need to worry about the Poisson distribution on the second page. The only ones we care about are normal CD, inverse normal, binomial PD, and binomial CD. If you can get to grips with those and you understand how they work, what their differences are, and what the quirks are that you need to watch out for, then you should be pretty confident with most of the work on statistical distributions for A-level maths.